So this first video is just going to be the difference between ionic and covalent bonding, but we have differentiated the 3 different types of bonding up here. Now, ionic bonding could actually be between 2 non-metals, although we generally learn it is between a metal and a non-metal because that is almost always the case. But it can actually be between 2 non-metals, and you will come across examples at GCSE when that is the case. So I mention it now, so as when you see that, you don't get confused. But the key point then is for ionic, and I haven't really gone into covalent too much at this stage, and maybe I'll include it on this video. The key point is that ionic is between a positive and a metal ion being attracted to one another, and then they form this kind of never-ending lattice where a negative ion snaps into that place and a positive ion snaps into that place, and so on. And this is a lattice, not a molecule. And so the formula is not called a molecular formula because there's no such thing as an ionic molecule. But a formula, this one would be a molecular formula because it describes the structure of a molecule of water in this case. So let's look at, I briefly introduced this word empirical formula because it has a kind of parallel with what an ionic formula is. An empirical formula simply describes the ratio of one element to another within the molecule, or within the substance. So butene is C4H8, and so because it's got 4 carbons and 8 hydrogens, and so the ratio is 1 carbon to 2 hydrogens. So this would be the empirical formula. Essentially, the ionic formula is always the empirical formula. Now, what I haven't included in the first part, when I'll include it in the video now, is how to construct ionic formulae from what we understand about the different elements, and also much about covalent. So I'll include this in the recording. If we go back up to this periodic table, remember what the group tells us. So I'm going to assume that we know that the group tells us the number of electrons in the outer shell. So group 1, I won't bother explaining how we can see that, but if you'd like another lesson on atomic structure, I can go over that and the periodic table. But so the lithium has 1 electron in the outer shell, as does sodium, as does potassium, rubidium, cesium, and francium. And these all have 2 electrons in the outer shell. Strange block of transition metals in the middle. Notice it doesn't have a group number. That's because it can form more than one type of ion. And it's confusing to ask the question how many electrons are in the outer shell. When you go to A level, it gets a little bit less confusing. So for now, we don't worry about the fact there's no group number in the transition metals. So over onto group 3, these have 3 electrons in the outer shell. And 4, 5, 6, 7, and 0. 0, well, that just means it's got a full outer shell. Now, atoms are always trying to have full outer shells. So if it's really easy for them to either lose 1 or gain 1, it's going to be very reactive. Losing 2 or gaining 2 will be a little bit harder, and losing 3 or gaining 3 will be harder still. And so those ones are going to be less reactive. So the most reactive metals are going to be in group 1, and the most reactive non-metals are going to be in group 7. So why is group 7 generally, apart from this one down here, why is group 7 generally non-metals, and why is group 1 metals? Or in fact, why are ones on the left metals and the ones on the right non-metals? What is it that makes something a metal and makes something a non-metal? Well, a nice way to think about it is that metal atoms form positive ions. That's one way we can think about it. Another thing we could say is that metal atoms have a small, and all these different sentences are connected, right? Have a small number of electrons in the outer shell. Now, I've already said that atoms like to have full outer shells. So if they've got a nearly empty nearly full outer shell, then it's going to be, it only needs one more to fill it up. And if it's got it's got a nearly empty outer shell, well, it can, like group 1, it can get rid of that outer shell, and the one underneath it would be full, and so then it would be happy as well. So let's draw lithium, for example. Lithium, we're just going to do the Li in the middle rather than doing the nucleus. We're just interested in the electrons for this explanation. Now, when you draw these diagrams, you don't actually have to draw the first shell. You only have to draw the outer shell. But I'm going to draw the first shell just so you can see it more easily. It's got 3 electrons because it's got an atomic number of 3, so therefore 3 protons, and 1 in the outer, and so it's got 2 in the first shell, 1 in the outer shell. I would avoid saying that the atomic number tells us how many electrons. It sort of does, but the reason why that is not a good way to think about it is because if I drew the atomic symbol for lithium, so we'll do the atomic number down at the bottom, mass number at the top. These can switch around and often do. If we lose an ion, which in fact this is what would happen, because it wants to form a full outer shell. If it loses an electron, I think I said if it loses an ion. If it loses an electron, it now loses that entire shell, which means it's now got a full outer shell, right? So it's lost that electron, and this electron's going to go somewhere else. And we can draw this like this. But we don't actually have to draw the first shell, so technically we should draw it like that. And if I wanted to draw it without, in this other way, sorry, this plus here just means there is also this spare electron that's floating about at the moment. Then what I would do is just do a little plus like that. But notice that the atomic number still says 3. It still has 3 protons, that's why, but it doesn't have 3 electrons. So it's not a good idea to start getting into the habit of saying that the atomic number tells us the number of electrons, because in this example, it does not. Okay, it tells us the number of protons, and if it's an uncharged neutral atom, then that is therefore also the number of electrons. Okay, so we've got our positively charged lithium ion. Let's take a non-metal atom, so they're a very metallic, I suppose you could say, very metallic one would be all the way on the left, a very non-metallic would be all the way on the right. We're not going to do these ones. Why are we not going to do these ones? Let me pause the video and see if somebody can tell me why I'm not going to use group 0. So I'm not going to use these noble gases because they already have a full outer shell. The 0, you could think about it as only 0 in the outer shell, but therefore that's not the outer shell if there's nothing in it. So but therefore the shell underneath would be full. It doesn't say group 8. Anybody want to tell me in the chat why we don't call group 0 group 8? Okay, well the reason why is because helium doesn't have 8 in the outer shell, it's got 2 in the outer shell. But what they have all in common is they all have a full outer shell. Okay, so we've got a lithium here. I'm going to take chlorine is the one that I decided to choose. So chlorine is in group 7. Therefore it's got 7 in the outer shell. I can't remember how many other electrons it's got. I'm only interested in the outer shell anyway. And I'm not going to use crosses. Most of you will probably know why, because we're going to do a dot cross diagram. So we're going to show how the electrons are moved from one place to another. So there's our chlorine atom, a neutral chlorine atom. You won't ever see it on its own like this because it's got this nearly full outer shell, so that's not going to work. The electron that came from lithium could be donated to the chlorine atom, thus making the chlorine outer shell full, but at the same time it makes the chlorine atom an ion. Now, strangely enough, the lithium atom became a lithium ion, so it gets to keep its name, but the chlorine atom becomes a chloride ion. So the negative ions, well, actually, let's just say the non-metal ions lose their name changes. So that's a chloride ion, and so that's negative. I said I was going to. It's a little bit messy. I'm just conscious I want to get through as much as possible. So I said I was going to color code these, didn't I? So let's color code that like that. And chloride ion. And I'll color code that like that. Okay, fine. Okay. That's being difficult. Okay, so one more time. Okay, I don't know why that's not letting me color it all. Never mind. So that's our chloride ion. And basically you would do the same sort of thing. Whatever the mass number and the whatever the mass number is and the atomic number, you'd write that and then do the little minus up there. The main thing is this thing up here that I'm interested in. So this is really the dot cross diagram, and so you could just write that as like this. Oh, and you could also even do it without the circle, by the way. So like this. So you may see this sometimes. You don't see it very often, but you do sometimes see that. So that's our lithium chloride. Now, we have a positive +1 and we have a negative 1 charge, so they work 1 to 1. But some of them do not. Okay, I'm aware of time. I'm going to try and speed up here. So let's see, if we look at like magnesium, that's +2. If magnesium reacted with oxygen, would be 2-. That would also be 1 to 1. No, it wouldn't be Mg2O2, right? Because we only need one magnesium ion for one oxide ion. 2 + to a 2-, so it'd just be MgO. Whereas if I had a magnesium ion with, let's say, a chloride ion, well, that would be 2+, because it would lose 2 electrons, forming a double positive charge, and this would be 1-. So I'd need to have 2 chloride ions for that one magnesium ion, so that would be MgCl2. So there is a bit of practice we could do if we had time to focus on this topic a little bit more, building up to, if you want to practice this yourself, the classic, most difficult one that's usually given is aluminium oxide. So I think what I'll do is I'll stop the video there actually, and then I'll do another video talking about covalent compounds.